Hi, my name is Paul from Physics High, and today I want to talk about the photoelectric effect. Now, before we start, please remember to press the button to subscribe and maybe consider buying me a coffee if this video ends up being helpful for you. The link is in the description below. I go into a much greater detail of what the photoelectric effect is, as well as the events that led up to the understanding of the photoelectric effect. So please look at my series of videos. The link's either in the description below or that link up there. But let's quickly review what the photoelectric effect is. Now, basically, if I have a particular metal, let's say we are going to call this metal sodium. If I shine light on it, what happens is I have electrons that are emitted, and we call those photoelectrons. And the idea of the experiment in terms of the photoelectric effect, it actually validates a model of light that says light has particle-like behavior. In this case, we can explain the effect here by treating light not as a wave, but light as discrete quantities, which we refer to now as photons. And so what we end up having is that my light is now result of a series of discrete numbers of photons. And what we end up getting is that the number of photoelectrons being emitted is equal to the number of photons I actually get. The photon imparts its energy to one and only one photoelectron as long as the energy is greater of the photon to enable it to be released from the sodium atom. And so as a result, we have this idea of the work function, that minimum energy that the photon needs to have in order for my electron to be emitted. And so we now get a mathematical formula that Einstein was able to demonstrate. The kinetic energy of my photoelectrons is determined by the energy of my photons, which is HF. You subtract the work function, which is the value of the minimum energy over here. Now, what I can do is, instead of saying this, I can actually also call it this HF. Naught is in this case what we call the threshold frequency, which we're going to talk about in a moment. The point here is to show you that what actually results in the increase in kinetic energy is not the intensity of the light, it's actually the frequency of the light, because it's frequency dependent and not intensity, which is intensity simply is how many photons you actually get in the first place, and that does not affect the actual outcome of the velocity or the kinetic energy of my photoelectrons. Now, if I graph all this, I'm going to have on my y-axis, I'm going to have the value of energy, and on my x-axis, I'm going to have the frequency. What we end up getting is a graph that looks like this. It's a linear relationship, and that's consistent here. You can see what we have here is a linear relationship of y equals mx plus b. If I pass this on over here, my threshold frequency ends up being equal to the negative value over here, the coefficient over here. This dash right here, is basically, this is the minimum amount of frequency I need for energy to actually exist in my photoelectrons. Well, that's my threshold frequency, which I mentioned a moment ago. And finally, you can see that this has a relationship where h is actually the gradient of our graph. Well, that is exactly h here. That is Planck's constant in this particular relationship. Now, I won't go into this great detail over here, but the determination of the work function can be done by experimental methods, by setting up a photocell that has the photoelectric effect taking place and then adding what we refer to as a stopping voltage. In other words, applying a voltage in the opposite direction to work out the very bare minimum of energy for the photoelectrons to be emitted, but explore that more in my videos, which is in greater detail. I hope that has helped you briefly understand the photoelectric effect. My name is Paul from Physics High. Take care and bye for now.